All right, everyone. So thanks so much for showing up to the second session. Our first talk in the second session is from Cameron Moy, and the talk is about teaching language for specification. So thanks, Cameron.
Thanks. Everyone can hear me all right? Good? Okay. So yeah, I'll be talking about a new teaching language for software specification, which is intended for a course that we have at Northeastern. I should first mention that a lot of this work is done in collaboration with Daniel Patterson. So I worked a lot in the background working on this programming language, but Daniel's actually the one who was teaching the course and came up with all of the material, and so he's really the mastermind. I was kind of working in the background, so he deserves as much credit for all of this. Okay. So to give you a little bit of background about the context, so we're at ICFP and the Scheme workshop, and I think a lot of us think formal specification is really important. In a language like Racket, we usually will use something like a contract in order to have a specification for our programs. And we like to write really rich specifications so that we get nice error messages and we can test our software. And so we would like to teach undergraduates this. I think there's lots of universities that would like to bring this into, or already have brought this into, the undergraduate curriculum. And there's a lot of ways that you can think about bringing in software specification to undergraduates. And one common approach, I think, and we saw in some other talks about this, is proof assistance. So you can teach proof assistance like AGDA or Lean. And there's plenty of resources and textbooks to do this, and plenty of courses that do so. And this is great, and lots of students find this very engaging. I certainly did as an undergraduate using Software Foundations. I found that to be a really great experience. But there are some drawbacks. And one of the drawbacks is there's a quite large learning curve, especially when you're using some of these more advanced proof assistants. And this is the same kind of experience that we've had in ordinary teaching for programming, which is, introductory curricula often will use industrial strength programming languages like Java. And of course, in the Scheme community, we know that having a more minimal programming language is often very helpful. So this is where a lot of, for example, how to design programs comes out of, which is the realization that you want pedagogic programming languages, and maybe even a sequence of pedagogic programming languages, in order to build you up eventually to an industrial strength language. And that's useful because you get, for example, good error messages out of that. Okay, so proof assistants have a steep learning curve. We might want to avoid that. Another problem, which is if you're teaching in an undergraduate setting, and especially to maybe like freshmen who have just, for example, learned functional programming, there's potentially insufficient time to actually specify properties of interest. If you've just come out of your first programming course, and then you're now trying to learn a new proof assistant, and you have to learn all of this new syntax, and it's quite a heavy burden. And that means that a lot of course time is going to be spent on the tool, and not so much on the specifications. Okay, so you may end up at the end of the course only getting to a couple of very simple properties. And so we would like to be able to specify something that's a little bit more complex. And the last thing that often we hear from students, and I've actually talked to plenty of students who've took prior iterations of the course that we have at Northeastern, is that they find that when they go on internship, they find that they're not using any of the skills or many of the skills that they learned in the logic course. That the experience of using proof assistant, they feel like they didn't get a takeaway from that, that they could use on the job. Okay, so we would like to try to address some of these things. Okay, so just a little bit of context for where we're coming from. So at Northeastern, we have a curriculum that looks sort of like this. It's a little bit small, but hopefully that's all right. The first course is this Fundamentals 1, which is based on how to design programs. And then the intention is that you follow this path along the right. So you go to Fundamentals 2, which is taught in Java, at least at Northeastern, object-oriented design, which is kind of scaling up the things that you learned in fundamentals too, and then software development at the end. And there's this kind of parallel track which is required for quite a few students, but not all of our students, which is to take logic and computation. And exactly when you take it is a little bit unclear, but you can take it immediately after Fundamentals 1. So what's interesting, at least from our perspective, is that in the course we get some people who are freshmen, so they're in their spring semester of their freshman year, and we also get seniors, okay? So we have a very kind of mixed audience when we're thinking about logic and computation. And so we have to assume both that you may have students with a kind of minimal background in programming, but also we want to make it sufficiently interesting for seniors who have done 2 co-ops and have seen a lot of programming. So we want to make it interesting, but not too difficult for everyone. Okay, so that's the context that we're in. So what is the solution? Well, I kind of hinted at it, which is this logical student language, which I'll refer to as LSL, which is a teaching language that's based on ISL from How to Design Programs. So the idea is if we want to minimize the time that we spend on teaching the language, we're going to build on a language that students already know. So we're going to minimize the changes from ISL, which they already took in Fundamentals 1. We're going to add some new features, but not too many, not a completely different context. So basically, almost from day 1, assuming that the students still remember things from Fundamentals 1, which the freshmen do, but maybe the seniors a little bit less so, that we can start talking about specification and the actual skills required in the art of specification, as opposed to the details of how to use a particular tool or language. And the idea is this will smoothly integrate with the rest of the curriculum. Okay. So what does that look like in practice? So the language itself is intended to support this key idea, which is that students will write specifications and then gradually increase the confidence that software conforms to this specification depending on how much effort they want to put in, okay? So in Fundamentals 1, if you're following how to design programs, you're going to follow this design recipe. And one of the first steps in the design recipe is writing a signature and purpose statement. And this signature and purpose statement, they're in the form of comments. So you write a function and you have this signature and purpose statement above it. And the intention is to do this in a very systematic manner. And that's what the course goes through. But we want to demonstrate in this course that you get a lot of value out of going from an informal specification to a formal specification. And we want to make that gap as small as possible, syntactically. So the language actually expresses the specifications in a language that looks very, very similar to the informal comments that students would write in Fundamentals 1. And those end up being contracts. So the contracts are intended to mirror the language and the syntax that the comments would in Fundamentals 1. Except now it's a little bit more formal because they're actually executable. And so once you go from informal to formal, from comments to contracts, that's the first step, then we talk to students about, well, what does that buy you? Because of course, that's a little bit of effort to go from informal to formal. And if you want to specify richer properties, it may take you quite a while to get to something that is specifying all of the properties that you would like. So what do you get from this? The first thing that you get is you get them checked. So contracts typically are runtime checked. So you write down the contract, you have your program, you write down some tests. You may write a larger program that uses a lot of the functions that you've written. And then when you run the test or run the program, those contracts will be checked at runtime, which means that if some of the properties are violated in one of the tests that you've written, for example, a unit test, you'll know about it, and you'll get some information and some blame about which part of your program violated the specification, okay? So that's one thing that you get from the contracts that you wouldn't get from the comments, okay? The second thing that we emphasize immediately after that is that you can actually use these contracts for property-based testing, okay? So, contracts are usually run in one mode, which is this checking mode. But it turns out that you can often run them in a different mode, in a testing mode. So if you have a contract, typically, at least for first-order contracts, it's a predicate that takes in values and checks to see if that value satisfies the predicate, just a Boolean true or false. But a contract can also combine the predicate with a generator. So you can say, oh, is this an integer? But also a contract can say, okay, well, I have a way of generating integers. So it can combine these two things, which means that your contract system can double as a quick check-like thing. So if you put a contract on a function, and those contracts all happen to have generators associated with them, then what you can do is you can say, all right, I want to quick check this function, and then you can test it like you would in Haskell, for example. Now, of course, that's assuming that all of your contracts have generators associated with them. So for the standard library that we provide students, all of those have generators associated with them, more or less. But we also tell students how to write generators. So if they define their own first-order contracts, there's a way of specifying generators on those first-order contracts. And we talk a little bit about what does it mean to have a good generator, et cetera. And then they can use that to test their programs as well. So it's a very nice way to go from just runtime checked contracts to also being able to do property-based testing with very, very little additional work. Okay, and then there's another step that we like to do at the end, if possible, which is doing verification. Now, I put verification in quotes because it's maybe not as solid as doing something in a proof assistant, but we have some very lightweight kind of verification via symbolic execution, which we can do for certain limited circumstances. So for example, we tell students how to finitize some of their contracts, say, for example, having lists up to length 3, for example, and we can verify that certain functions work, say, on lists of length 3. So that gives you some confidence that for at least some inputs, some smaller inputs, you actually can verify that your code actually satisfies the contracts. And in some cases, you get full verification if you don't have, for example, operations over lists, just integers. So this is done via Rosette. So Rosette is a symbolic executor for Racket, and so we can use that to do some simple contract verification. Okay, so there's another little step at the very, very end of the course, which we give students a taste of, which is actual verification. So at the very end, there's 1 or 2 weeks where we switch to Lean to show what it looks like to actually have a little bit more heavier weight verification, so that students can actually transition into subsequent courses which actually go into the details of how to use a proof assistant and actually prove properties about programs. Okay? So the general idea, I like to think of it as this kind of gradient, which is on the left-hand side, you have checking, which you get automatically, basically for free. And on the right-hand side, you're getting more and more kind of effort put into it, but you get more out of it. And at the very, very end, on the right-hand side, you get fully verified software. But we don't insist that you are at the right end of the spectrum all the time. We're kind of showing you all of the parts along this spectrum. So you can choose, depending on how confident you want to be in your software or what your time constraints are, where you want to sit along that spectrum. And we think this is a pretty practical way of teaching software specification. And hopefully, this kind of do as much specification, as much verification as you want, ends up being useful for students on their co-op and in practice. Okay? Okay, so some of the advantages, I think I've mentioned a few of them, but little to no time talking about language features. That's a big one. We jump basically straight into talking about specification. An explicit connection with practical skills. So one of the things that we do, of course, if you have a teaching language, oftentimes students are saying, well, this is silly. I'm not using, the most important industrial strength programming language, and they're a little bit unhappy about that. So what we try to do to mitigate that is to connect the concepts and things that we teach in the course with languages and tools in practice. So one thing that we do a few times during the semester is say, okay, you've learned how to do property-based testing in this teaching language. pick whichever language that you want to use, one that you've used on co-op or one that you're interested in. A lot of people pick Java and Python and things like that. Find a property-based testing library in that language, and then do some of the exercises, do some of the homeworks that we've given you in the course in that language and in that library, and reflect also on what your experience was doing that. And the idea is that by actually having students use tools that are used in practice, that they'll come away with the feeling or some skills that they can actually apply on the job. The final thing to mention is that our goal is to be able to write interesting properties, and so we were able to do that. So we have some homeworks, for example, having students write a simple memory allocator and a distributed snapshot algorithm. So in the simple memory allocator, you can specify things like you're not going to have a use after free, or in the distributed snapshot algorithm, you ensure that when you take a distributed snapshot, it's actually a consistent snapshot of the system, okay? So just remember that these are programs that we're having freshmen write sometimes. And we're actually able to talk about properties of those systems. And that's really the goal of using a language like this, is to be able to get to some really interesting properties. Okay, so let me talk a bit about the structure of the course. So probably a lot of you are familiar with the design recipe, which goes something like this. So on the left-hand side, you have steps of the design recipe. And along the top, along these columns, you have different kinds of data. So you start with atomic data, like numbers, and you go to more structured data, mutually recursive data, et cetera, et cetera. So in the course, in Fundamentals 1, you kind of go along these columns. You start with the atomic data, and you go through all the steps of the design recipe. Then you move on to more sophisticated kinds of data. And then by the end of the course, you're operating over pretty sophisticated kinds of data. And so we kind of would like to try to follow this recipe as much as we could in Logic and Comp. So kind of the first half of the semester, we do a very similar structure, but with a modified design recipe. So we're talking about atomic data, unions, compound data, recursive data, functions as first-class values. And then we talk about all of the kinds of specifications that you can write over that kind of data, what you can do with it, property-based testing, et cetera. And then in the second half of the course, after the spring break, then we talk about more sophisticated kinds of properties that you would write in general. So talking about, for example, data abstraction, temporal properties, properties about effectful programs, properties about concurrent systems, about resources, which include performance constraints, and then at the very end, some theorem proving. So that's kind of the topics on the left, and then on the right, we're having the kinds of language features and tools that we use in order to specify the things on the left. So a lot of contracts, for example, ordinary predicates, unions, struct contracts, recursive contracts, dependent function contracts, which is really important. You're specifying rich properties to be able to do that. Data abstraction, there's parametric contracts, both for existentials and universals. So we get to talk about modules and things like that. Difference between that and OO. Temporal specifications, so this is kind of interesting. Earlier in ICFP, I gave a talk about trace contracts. So we actually have a very simplified implementation of trace contracts in the language. So we're actually able to get kind of cutting-edge research into these teaching languages, and students are actually able to very easily use these things. And then we also teach them about concurrency. So in the first course, they don't know anything about concurrency, and we teach them a little bit about the actor model, and then how to specify properties about concurrent systems. We also talk a little bit about empirical evaluation. So one of the things that we think is really important is to actually check in practice that your programs are satisfying the properties. And one of the things that you can do is if you think that a function has a particular complexity class, you can actually look at it. So we have tools for graphing performance numbers and things like that. And that's a kind of property as well. It's not just contracts, it's also other kinds of kind of intentional properties that you might care about. And then, of course, at the very end, we do some lean. Okay, so I want to give you a little bit of a demo of some of these things. So I have Dr. Rackett here. I'm just going to go through a couple of the sort of exercises and code snippets that we show students in the course and show you what they do. So this is what the language looks like. It looks like ISL, if you've ever seen ISL, or looks like Scheme. The difference here is that we have this colon form, which allows you to attach a contract to any of the functions inside of your buffer. And so here we have an example of a dependent function contract. So what you're saying is here we have a list of arguments. The first argument is a natural number. And this is a function that computes subsets. So you give it a number between 1 and n, and it will compute subsets of n, all the possible subsets of n. So we want to guarantee that the number of subsets that you get back is 2 to the dn. And we do that with this results contract here. So it's going to depend on the argument. And we want to make sure, well, you get a list of lists back of natural numbers. And we have this extra constraint that we want to enforce, which is, well, what the length of that list is going to be 2 to the n. Okay? So that is good. I can just show an example. So subsets 3. You can see all the subsets there. And what we can do, I mentioned earlier that you can do property-based testing if you write this contract, and that includes dependent function contracts. So this check contract form, you provided a function which has a contract on it. And what it does is it will look at all of the contravariant positions of the contract, and it will generate for those positions. And then for all the covariant positions, it will be in checking mode. It will check that the thing works. So this is going to, for some amount, I don't remember how many it is, like 100 random inputs, random natural numbers, it will check this output contract. And we can see that it was successful. So if, for example, you made a mistake and you said, 3 to the n, then you would get an error. And it gives you a contract violation that says, oh, well, here was the example, the counterexample. If you did subsets of 1, you would get the following contract violation. It tells you what the output was. Okay? So that is a very simple program. Here's another one. So we try to make these contracts mirror what the comments are like in how to design programs, both for signatures but also for data definitions. So here's the definition of a tree from how to design programs. It's either a leaf, one of a leaf, or a node. And so here's the contracts for that. So you can see how we're trying to minimize the distance between the informal and formal. So we use the same language, for example, one of, for itemizations. So we can see you write some predicate over, it's int trees. You can write a generator. So we have students write these generators. And then you can combine those two things into a contract. And then this check contract for the int tree contract will actually use this generator to generate things. So we can see that. We can see that here. So we have some unit tests and also a property-based test. So once again, if I make a mistake, it will give me a counterexample. So you can take this counterexample, and it's formatted in a way that you can copy and paste it into the REPL and actually see the contract violation. Okay, let me run through a few more of these. So I want to show you the symbolic execution bit. So here is a function which is supposed to multiply numbers together, but for a very weird input, it's going to give you 0. Okay? Now, ordinarily, if you just try to do property-based testing on an input like this, you're never going to find this bug because, well, it's very unlikely that you're going to get that as the input. But if we run a symbolic executor, of course, it will find that. Okay? So we can see that Rosette, in this case, gave us a counterexample, an explicit counterexample, because it's able to symbolically execute that function. Okay? So that's a taste of what this is like. Let me conclude. So there's plenty of more work that we want to do. So this programming language, this was the first, last spring semester was the first time we used it. And we have plenty of things that we want to add to it. So ideally, we would like to perhaps integrate theorem proving into this teaching language so that we don't have to jump to lean, for example. We would like to have contracts that enforce some of these performance properties. So I said, you know, we have tools for graphing performance, but we'd actually like to have contracts for that as well. We would like to be able to do symbolic execution without always having to finitize the inputs. So that would require something a little bit more general than what Rosette gives us. We would like to have fewer gaps between ISL and LSL. So I didn't mention this, but LSL actually kind of recreates all of ISL because it's kind of hard to build on the teaching languages. So we'd like to make that a little bit of a smoother transition as well. And we're interested in going into a little bit more detail about property-based testing and talk about the subtleties with writing generators, of which there are many subtleties with writing generators. So if you're interested, all of the course materials online at that link, and the language itself is on the package server, the Racket package server, and you can find it. It's completely open source there as well. So there's tons of lecture notes and homeworks, and all of those things are publicly available. So you can, if you're interested in a course like this, you can use that, and certainly get in touch if you're interested as well. Okay, thank you. Yeah. So we would be doing something very, very simplified. So we only have a kind of 2 weeks, at least in the prior version of the course. We only did the proof assistant for 2 weeks. So we would only need something that very, very, very basic, not something that you would actually do any sort of sophisticated proving in. So you could use something a little bit more simplified. So I know, for example, there's the little typer has an implementation of dependent types called pi. So you could think about implementing something that and integrating that, but something very, very simple. Yeah, but we're not totally sure about how to do that. Yeah, but, yeah.
More questions?
What do the students think of it? Do they like it?
Yeah, so from anecdotal evidence, they really enjoyed the course, and certainly compared to, so I actually, we did some interviews with prior students who gave us feedback about their experience in the course, and just qualitatively, students who came out of this course were much, much happier with what they learned and thought they could apply it in practice. So that's just, but that's anecdotal, but yeah. Yeah, so almost everything is inside of the language. Actually, we did all of the exams in the language in Dr. Racket. So there's almost nothing on paper and pencil other than there's a few things that we did trying to connect some of the ideas with paper and pencil proofs at the beginning. So like propositional logic, doing truth tables and things like that as a refresher from discrete math. And also connections with doing ordinary proofs and inductive proofs. And that connection between writing recursive functions and inductive proofs. So we did a little bit of that connection on paper, but almost everything is done inside the editor. Yeah.
Any more questions? I guess I have a final question, which is just that in teaching a course like this, one of the main things I really hope to convey to students is teaching induction, basically. And I think you were kind of pointing this out. My concern when I started to see the talk was that you might eschew that if you weren't teaching improved assistance. And so what do you think, how do you think this course kind of addresses that? What would you do in the future to kind of solidify that?
Yeah, so this is a concept, I think, so how to design programs itself, Fundamentals 1, talks about recursion in a way that if you also take it at the same time as discrete math, you are forced to see that they're the same thing as induction. And so we do try to make that connection a little bit explicit in the course as well. Probably we could do a little bit more of that, but it is something that does come up, and there's a whole lecture like making that very, very explicit. Yeah.
Thank you.
Yep. Thanks.
All right, thanks so much. Let's take a seat here again.